Hi, my name is Tapas, and today we are gonna. He's Kushal, he's Pardakeshwar, he's Suhas, and today we are gonna talk about auto scaling as a service. We are gonna talk about the feature list implementation, the system architecture, and we are gonna see what we have done in the demo, and then we are gonna move to the management features. So, say an application is hosted on a VPC, and for some amount of time we see an excessive load for that particular application. What do? We can add additional resources, but there's a problem with that. We need to maintain those resources even when the load goes down. So how do we better implement this solution? We can use auto scaling as a service. What we can do is, whenever the load goes up, we'll just leverage the resources of another VPC to add additional resources there and host the same application there, so that for whatever amount of time, for whatever excessive load, the new VPC will take care of all the additional load coming in, keeping the system online for most of the times, maximum number of time, and keeping the downtime very low. How is this better than the previous approach? It's cost effective. Whenever the load goes down, we can just remove the resources and we can scale down the application. That way, the customer doesn't have to pay for the additional resources for that whenever the load is down. Uh, Next, let's move on to the feature list implementation. So when do we scale up? Metrics to that. So steal time. We are considering steal time to scale to determine the as a metric to determine when the system is high on load and when the system is not. So we have a maximum threshold for the steal time. Whenever the steal time for that particular system goes beyond the maximum threshold, we will scale up. Where do we scale? But for containers, let's talk about this also. For containers, we cannot consider steal time for obvious reasons. So we will use average CPU usage for that container as a metric to determine the scale up and scale down for that particular container. Now, where do we scale? You We'll have a list of hypervisors, which we'll just go through the list of hypervisors and we'll determine which hypervisor has lesser load based on the steal time, and we will decide on which hypervisor we can add the additional resources for the additional load. Now, when do we scale down? So we'll have since we had a maximum threshold for the steal time, we can have a minimum threshold as well. What we can do is, when once the steal time for all the resources goes down beyond goes down goes lower than the minimum threshold, we can just scale down and we can remove the scaled up resources, so that the scale down and we can remove the scaled up resources, and we also have cooldown period for both scale up and scale down. This is because we should not take decisions randomly. We need to keep a cooldown period so that the decisions are taken wisely and not just based on parameters. This cooldown period will help us taking decisions wisely by keeping the resources intact for some period of time. Now Kushal is going to take over the next couple of slides.
So I'm going to discuss the system architecture that we've implemented as part of this project. Couple of things. The first thing that I'd like to talk about is the namespace that we have used. So we have a namespace for each tenant that is there within a hypervisor. So this gives an L3 isolation between the tenants itself. Now we have another, we've used bridges to implement the subnets within a tenant. So that provides L2 isolation within the subnets of the tenant. Apart from this, we also have a management network. So this management network is connected to a controller. So each tenant will have its own controller now. And this management network can be used to perform management operations. Apart from this, we have used CollectD to collect the steal time of all the VMs. So this CollectD data will also come through the management network. So now, let's say, since we'll be having VMs on multiple hypervisors that are within the same subnet, we have used VXLANs to achieve this, right? So each subnet will have a VXLAN to connect VMs on different hypervisors. Apart from this, there is another VXLAN to connect the controller VM that is residing on the main hypervisor to connect to the VMs that are on the remote hypervisors. So the management network is also connected over the VXLAN. So now let's go to the demo. So quickly, so I'll tell you what the windows are. So the left side window is the first hypervisor, and the left bottom is the second hypervisor, and the right side, both the windows are on the controller that we have for the VM. So we are taking a couple of inputs from the user in the form of a schema.json. So this is the schema.json that you see right here. Here, if you see, the important things are minimum steal time and the maximum steal time. So in this case, it is configured to be 10. And if you see here, another thing here, that's the status of the system that is currently going on. So it's currently idle right now, and there is no scale up. So there is no scale up time as of now. And the number of VMs that are there on each hypervisor. So on the first hypervisor, we have 2 VMs running, and on the second hypervisor right now, there is nothing running. So what we will demo is, we will be demoing excess load on these 2 VMs so that a new VM is created on this hypervisor. So we have used, as I mentioned, we have used collectd. So I'll be showing you the collectd logs. So right now, as you can see on the first VM, we see that the steal time is 0.0, and when you run our script, it says nothing to do. So no action has been taken because the steal time is well within the threshold. Now we'll be running a script to generate excess load. We've used TestNG for that. So now we're running load on the VM, so the steal time should go up. So the collectd reports that accordingly. So as you can see, the load has gone up, and when we run the script, it decides to scale up. The decision has been taken to scale up, and a new VM is being created. This VM should be created on the second hypervisor that we have here. So creating a VM takes up a lot longer than creating a container. So containers come up very quickly, but VMs take up a lot of time because it has to boot the operating system. So as you can see, a VM has been created named T1N1V3. So now let's check the hypervisor to see if that VM is shown up here or not. So as you can see, a new VM has been created here. So what we could see here was when the load on this hypervisor has increased, it went and decided to scale up on the second hypervisor. So a lot of things happen when we create a new VM. So apart from all the configurations, one thing I like to highlight is the collectd configuration that we do on the VM. So when the new VM comes up, we enable collectd on that, and that has to report all the data back to the controller now. So each VM reports its data back to the controller, so controller can keep track of how much steal time how much load is there on each of the hypervisors, and take decisions accordingly. So as you can see, the IP for the new VM is highlighted here, and we are able to log into that. So the VM works perfectly fine, and it can handle all the traffic that is coming in for it now. Another thing that I like to show is the collectd logs that are created for the newly created VM. So as you can see, as I've highlighted here, so you can see the new collectd log that is there. So that is all from the demo perspective. Can you open that? Yeah. So let's talk about the management features. So the first management feature that we have is the configurability. So when we onboard the tenant, so initially when we onboard the tenant, we take a input in the form of a JSON file. So he gives us the network design in that. So we create the network design for him from scratch, basically creating all the subnets for him. Apart from that, we also have another. We input so many thresholds, all the minimum and maximum steal time thresholds, cooldown periods. And so all those can also be changed during on the fly during runtime as well. Now the second feature that we have is dynamic monitoring. So we have exposed an API to give the snapshot of the current tenant system, right? So whenever you call this API, you get the JSON back. In the JSON, you'll have details about the current system state. Basically, if the tenant is using more resources, is he in the scaled up state, scaled down state, or idle state? How many resources he's using, on which hypervisors are his resources currently running on, right? So this data can be used by the tenant himself to monitor the current load on his application and different events on the system, basically when he was scaled up, scaling down. So provider can also use this data to monitor the resource usage by each tenant, and charge them accordingly, maybe for billing purposes, and keep track of it. So basically, to provide accountability. Now the problem with there is a problem here, that where do we store this data, right? So somebody has to store this data and provide accountability. So the tenant should not be able to modify this data, to fake the data and get away with all the additional resources that he's using, or the provider should not should not show that the tenant is using more resources than he's actually used. So nobody should be able to fake the data here. So we need to build a trust between them. So what can be done here is, a smart contracts can be created between the tenant and provider, saying that they'll be locking on the transactions, locking on the transactions that are basically the events that happened in the system when you scaled up, scaled down. So each of them is a transaction now. So all of these have to be locked. They cannot be modified anymore once they have been created. So one thing that comes in mind is using open source blockchain technologies to achieve this. So that's perfect in this scenario. So using tools like Hyperledger is a perfect fit here. So this approach actually provides accountability, and this management feature of ours enables us to to achieve that using Hyperledger. So that is all we have as part of this presentation. Thank you. Any questions?